example 2 here. Let's do another example. So we're going to use a table to estimate numerically the limit of 3x minus 2 as x approaches 2. Okay, so let's write that out first. Example 2 says use a table. Use a table to estimate the limit as x approaches 2. So they can change this number to whatever number they want, and we're going to 2 as of 3x minus 2. Okay, so this is just the function y equals 3x minus 2. Well, what kind of graph is that? It's just a line, right? So we don't need to put that in our graphing calculator. We can graph that by hand. So -1, -2, 1, 2, 3, 4, 5, 1, 2, 3, 4, right here. So I'm going to start at -2, which is down here, and then I'm going to go up 3 over 1 for my slope. So 1, 2, 3 over 1, 1, 2, 3 over 1, do it a couple times, and then I'm going to make my graph, my straight edge right here. The point that we really care about is where x equals 2. We want to look at what's going on at x equals 2. Okay, so what's the y coordinate when x equals 2? 4, right? 2, 4. If we're not sure, let's plug it in. So let's actually plug in 2 into here, since we want to find out what is happening at x equals 2. So 3 times 2 minus 2 is 6 minus 2, so that equals 4. Okay, so we do have the point 2, 4. Okay, what is the limit at 2, 4? It's 4, because when we plug in 2, we get 4. But what's the purpose of limits if we just plug them in? Well, sometimes it doesn't work that way. What we want to look at is what's happening to the line when we come in from the left side of the point and we come in from the right side of the point. Is it approaching the same number? 4. Yes, it is. Okay. We want to look at our table too, our table values. So if we were to put this in our calculator, we would get a bunch of numbers like this, right? And we would get 2, 4. But what we want to look at is what's happening to the left of 2 at 1.99, at 1.99, at 1.9. Is it approaching 4? Are the numbers getting bigger and bigger close to 4? Yeah. How about after 2 at 2.001, 2.01, 2.1? Are the numbers close to 4? Yeah, they're getting bigger than 4. So if these numbers are both approaching 4, then our limit is whatever number we plug in when we get 2. When we plug in 2 is 4. So that is our limit. Our limit is 4. Okay? So yeah, that's easy enough. The limit is 4. So this limit is 4. So you just plug it in. Okay, the problem comes when you plug in a number and you don't get the limit. Okay, like example 3 here. So if we look at example 3, here. Example 3, it says use a table to estimate numerically the limit, find the limit as x approaches 0 of x over the square root of x plus 1 minus 1. Okay, now let's plug in 0 into this function and see what we get. So when I plug in 0, I get 0 over the square root of 0 plus 1, which is 1, minus 1. So I get basically 0 over 0. Okay, what is that equal to? What's 0 over 0? It's undefined, and that's what he said in the video yesterday. It's not 0, it's not 1. Somebody said 0 in the video, and he like freaked out. No, it's not. 0 over 0 is not 0, it's not 1, it's undefined. Okay, so if it's undefined, that means there's some kind of gap in the graph at when x is 0. There's going to be a hole, or there's going to be an asymptote, or something funky is going on there. So what can we do to find the limit? We have to look at what's happening to the left of 0 and what's happening to the right of 0. And to do that, we're going to put that in our graphing calculator and look at the graph. Okay. So generally, what do square root graphs look like? Square roots of x, they look like like a sleeping parabola, half of a sleeping parabola, right? So let's see if this one looks like that. Let's go to our y equals, plug in our equation. Our equation is x divided by, and then you got to put parentheses. Another big thing about this is you have to put parentheses in the correct place. We're going to have to put parentheses around this whole bottom denominator, or else you're going to not do it correctly. It's not going to graph the correct problem. Okay, so parentheses square root of x plus 1 and your square root, and then minus 1, and then another n to your square root, right? So I put x divided by this square root minus 1, so this is my whole denominator right there. Okay. And now I'm going to look at my window. Let me look at my window. Yes, I think I do want to go from 0. Actually, we want to go around -1. Let me put -2 in there. And my x minimum, I think I only need to go to 10. So, and the 50 I think is too high. Let me change that to 20. And I think we'll be good if we do that. And let's graph this guy. Alright, so yeah, I do get like a sleeping parabola, but I've got a big empty space over here, so let me bring that window down a little bit. So I'm going to go to, instead of all the way up to 20, I could probably go to 5 or something, or 6. And then make it nicer. So that's a better graph, right? It's much better. Okay, but what we care about is when x is approaching 0. Okay, so we're going to look at the graph when we have our xy graph. What's happening when we get closer and closer to 0? What's happening to the left of 0 and to the right of 0? Okay, so to do that, we're going to look at our table, or we can do our trace too. We can do our trace. I can go all the way to 0. But I can't quite get there, or it looks like it's going to be around 0, 2, right? So I keep going. Is it around 2? Yeah, the numbers are getting closer and closer to 2. And, when I plugged it in, I didn't get a 2. I got 0 over 0, which told me nothing. But if I go to my table, I do second graph. Let's look at my table. Oh, I have weird table sets. So another thing you need to be able to do is second window and change your table set. I'm going to change my table set to like 0.1 instead of 0.06, and -0.3. If I start at -0.3, that's fine. So table set, and so I can see, 1.8, 1.8, 1.9, error. Error is my 0 over 0, and then 2.04, 2.09. So it should be a 2. If this continued in a logical manner, it would be 2, right? So that's why this limit, as it approaches x, is 2. As x approaches 0, is 2. Okay? And so, we get an error here, but we get like 2.04 here. We get 2.09. We get 2.14. On the left of 0, we get 1.94. And then we get 1.89, and then we get 1.83. We can see that from the left side of the graph, it's approaching 2, and then it's also approaching 2 from the right side of the graph. Now, I do want you to draw the graphs as well. So our graph started at -1, 1 right here, and then it went up to 0, 2. And there's a hole, though. There's a hole in the graph at 0, 2, so you need to put like an empty spot there. That hole doesn't appear in your graphing calculator. I don't know why your graphing calculator is not capable of putting a hole in it, but it's supposed to have a gap there, right? So there's no value at 0, right? If we do f of 0, it's undefined. But it does still have a limit. The limit is still 2, because the graph is approaching 2 from the left, and the graph is approaching 2 from the right. So it does still have a limit, even though the value at 0 is undefined. Does that make sense? Okay, that's the big thing. You can still have a limit even though there's no undefined value at 0. Okay, so let's look at another example. Let's flip to the next page, example 4. It says to let's switch pens, you can still see this. Example 4 says to use a graphing utility to find the limit. We want to estimate the limit of the limit as x approaches 1 of x cubed minus x squared plus x minus 1 all over x minus 1. So what do we do first is see if we can just plug it in and find our limit. So we're going to plug in 1 into all these x's and see what we get. Okay, we're going to get 1 cubed minus 1 squared plus 1 minus 1 all over 1 minus 1. I already see a problem in the denominator because when I get 1 minus 1, we're going to get 0 in the denominator, which means already it's going to be undefined. And then when we do this, we get 1 minus 1, which is 0, plus another 1 minus 1, which is another 0. So again, we get 0 over 0, which is undefined. So the value when x equals 1 of y is this becomes undefined. But there's stuff going on. Does it mean that there's not a graph? No, there's still a graph, right? So we can look at what's happening to the left of 1 and to the right of 1 to find the limit. So that's what we're going to do. So we're going to look at the table, and we want to go to 1, and we want to see what's happening. What's happening around 1? What's happening at like 1.1, at 1.2, at 1.3? What's happening at 0.9, at 0.8, at 0.7? Okay, we know we're going to get an error here, but hopefully they're going to be numbers that it's approaching a number. We can tell what that limit is. Okay. So to do this, again, we plug this function into our calculator. Again, you're going to have to put parentheses around the top and the bottom to, hold all that together. So I'm going to clear out my last function. I'm going to put x cubed, parentheses, forgot about the parentheses, x to the third power minus x to the second power plus x minus 1 parentheses divided by parentheses x minus 1 parentheses. Okay, so your numerator needs to be in parentheses divided by your whole denominator in parentheses. And let's see what this graph is. Let's see if we get a good graph here. If we might need to change our window. Oh, it's just a parabola, right? It's just a parabola. And we want to find out what's happening at 1. So we don't really care about the minimum here. We actually want to go, so I'm going to press trace and move it over to, oh, it's way over at 5 for some reason. So let me just type in 1. And it gives me undefined, right? So, there we go. So, I'm getting closer to 1, and it looks like it's getting close to 2. So, I go to 1, it goes right over 2. So, yeah, it's approaching 2 as I get closer and closer to 1. So, these values are like, let me go to my table setting, and you can see I want to go down to 1. Okay, so this is where I want to be. Here's my error, 1.4, 1.6, 1.8, so, 1.4, 1.6, 1.8, and then after 1 we get 2.21, 2.44, and 2.69, so you can tell that in between here is 2, right, so it should be the 0.12. So the graph looked like this. And at 1, 2, though, at 1, 2, there's a hole. So I should have put a hole there. But the rest of the graph is just a regular parabola. And from the left, it's approaching 2, and from the right, it's approaching the same number 2. So this limit, as x approaches 1, is still of f of x, of our f of x, is still 2. Even though the value of 1 is undefined, the limit is 2. Because it's approaching 2 from the left, it's approaching 2 from the right, it's 2. Okay. So that's how you find a limit. Okay, that's nice when these are nice functions. They're easy functions because they're all continuous, even though sometimes they have a gap. But sometimes they're piecewise functions. So we're going to look at example 5, a piecewise function. It says find the limit of f of x as x approaches 3. As x approaches 3. And this is our function f of x. F of x is equal to two things, not just one thing. It's equal to 2 when x is not equal to 3, and it's equal to 0 when x is equal to 3. This reminds me about like a coding that you could do, because you could code things and you could say if the user answers yes, make it, you know, equal to. If the user answers no, then make it equal to 0. Alright, so what does this mean? It means our function is y equals 2, right? F of x is just another way of saying y equals 2 when x is not equal to 3. When x is equal to 3, then the function is equal to 0. Okay. So when x is not equal to 3 and when x is equal to 3. Well, y equals 2, that's just a straight line, right? That's just a line. Let's say 2 is right here and 1 is right here. And the only time it's not equal to is when x is 3. So I'm going to go 1, 2, 3. And I'm going to put a hole at 3, 2. And the rest of the time it is equal to 2. And it is equal to 2 like that. Okay. So left side, right side. What is it equal to when it is equal to 3? It does have a value. It's equal to 0. So 3, 0 is the point. So we're going to fill in 3, 0. So to the left of 3, it's always equal to 2, equal to 2, equal to 2, equal to 2. Drop down, equal to 0, back equal to 2, back equal to 2, back equal to 2. So it's mostly always equal to 2, except for one time. When is that one time? When x is equal to 3. Anytime x is equal to anything else, it's equal to 2. Okay. So the question is, what's the limit? Is the limit going to be 2 or is it going to be 0? Okay, so the limit does not depend on necessarily the value of the function. It depends on what's happening to the left of the function and what's happening to the right of the function. So since the left is approaching 2 and the right is approaching the 2, the limit is actually equal to 2. So the limit as x approaches 3 of our function f of x is actually 2, not 0. Okay. So because we know f of 3 is equal to 0, but that's not the limit. Okay, that's the value of the function. So this is a case where the value of the function is different from our limit. Because again, we care about what's going on the left, it's at 2, and what's going on the right, it's at 2. If you looked at your table, right, it would just be a bunch of 2's, and there would be an error here in the middle. Like this would say 2, 2, 2, 2, error, 2, 2, 2, 2. So since these are all 2's, your limit is going to be 2. Alright, is there a time that the limit does not exist? Yes, there is. So a limit can fail to exist. So put limits that fail to exist.